I couldn't possibly.
No, it's hand-eye coordination. I've seen your tennis.
Proves my point. All right. Welcome, everybody. Thank you for coming to this the Distinguished Seminar Series. Today is actually one of our own. Dr. Stier, Michael Stier, is a Lamb professor in electrical engineering, and he's been with NC State for 20 some odd years. And I won't
very odd
specify. I won't specify the. He's a fellow of IEEE. He's got numerous awards. He was past chief chief editor-in-chief of the MTT transactions.
Would you like me to read that?
And he's done a lot of work in RF and in multiphysics modeling in general. He had the Presidential Young Investigator Award when they were called PYIs, and he had the bronze medal for excellence by the U.S. research, the U.S. Army research, for outstanding scientific accomplishment. And it's a pleasure to have you. Thank you for accepting to show up.
Thank you for asking me. Okay. All right, so I'm pleased to be able to talk today about work that started a long time ago, and of course it's being funded by an enormous array of projects, but it is important if you're going to establish an academic career to have something that kind of bubbles along in the background and you get funded to do all sorts of various things. So compact modeling, or multiphysics compact modeling, is pretty much that universal thing that's been going on for 20 years, and you know, funding has gone in all sorts of directions. Sometimes the work has been funded directly, depending on the political climate or the funding climate, and sometimes the applications have been funded. So I think we've come a long way, and there are quite a few people work directly with me doing their PhDs and master's degrees at the moment who contribute to this, and of course many people in the past. And I was going to try and do an acknowledgement sheet, and oh gosh, I knew I was forgetting somebody, so I didn't do one, but you know, lots of people have done this. So I haven't actually given a talk like this before, quite like this before. And when I started assembling it, I realized I had to take about 2 or 3 slides from nearly everything I've ever said. And I tried to make it a little bit smoother, but it is going to seem a little bit rough. But I didn't want to use something I already had canned because it only captured a small part of the problem. So moving already, this is just the title slide. Oh gosh, it's going to be one of those days, right?
Where's that picture?
Oh, that picture from? It's funny you should ask. This is Burleigh Heads in Australia. So I was born in Brisbane, Australia. I moved to Burleigh Heads when I was 2, and I grew up here. So I learned to swim here. So this is an excellent... Uh-oh.
Yeah, you're not supposed to touch.
Can I go back?
With your finger. Those are the things, yeah. If you want to touch it, you can touch it with a pen.
Okay. So that's kind of where I grew up. So and that's Surface Paradise in the background there. So that's the symbol we use for Freda at the moment. So it's a breadfruit tree. Oh, I'm glad I could get that one. Okay, so I want to talk about a compact modeling philosophy, and it is the heart and soul of electrical engineering, or if you think of circuit simulation, the way SPICE works. And we've taken the compact modeling paradigm and applied it to simulation, which eventually became a Freda program. So nearly everything we do, everything I talk about today, has been implemented in Freda. So I left out anything that doesn't work. I only talk about the things that are working. But we're going to talk about what compact modeling is. It's something that is unique to electrical and computer engineering. You don't see it in other disciplines. It's very much tied into our idea of what a circuit is. You know, a circuit isn't something that's real. We forget that. I guess when we're in second year or first year, you know, we just have to learn this stuff, and we don't want to ask too many questions, but it's an invention, it's an abstraction, which is between the physical world and the mathematics. And our compact modeling paradigm, or the way SPICE works, fits in to that abstraction that's right in the middle there between the physics and the mathematics. And It's surprisingly good. We're very good at it. We can simulate very easily with it. We can conceptualize circuits very easily. If you're a circuits person, you can look at something that looks incredibly complex and you recognize the pattern. You know a transceiver when you see one. You know a differential amplifier when you see them. You know logic gates when you see them. And so we can amass a huge amount of data. So it's like this tremendous abstraction as well that fits in perfectly with the way we take information in through our eyeballs. So I want to talk a little bit about that. I'm going to ramble on and on, but I know Hamid will tell me when to move on. So Freda, how did Freda really start? Freda started more or less as a circuit simulator back in the early days. When you start your academic career, you tend to work on kind of niche problems, more or less in the mode of, hey, I can do better than what the person did in that other paper. But eventually you move on and you move into trying to come up with some great philosophy. And for those of you who write a dissertation, you do all this work, and at the end you try to think, you get really scared because it's not really telling a story, and then you try and pull everything together to tell a story. Well, the story that I came up with is multiphysics modeling, and it really describes it quite well. The way we do multiphysics modeling outside of electrical and computer engineering, or really anything other than a SPICE type simulator, is that we build up a great big finite element program and we write equations for each of the nodes, and we write the equations for whatever physics we're dealing with. So a large number of companies who are out there selling multiphysics simulators are basically selling finite element solvers, and sometimes they give you the equations for the different physics, and sometimes you have to write your own equations, and you are limited to the size of the problem you're going to look at. Basically, a million unknowns is what we can deal with finite element programs. So if you're going to do a volumetric discretization, you have an inherent limitation. If you use a compact model, which basically each model includes a lot of physics, you can look at much bigger problems, and you can also set things up to guarantee that you will have convergence. Never get into a problem with convergence or an accuracy problem. You can set things up that way. So not all compact modeling programs will do it. That is, be able to handle unlimited size problems or give you unlimited accuracy. But one of the philosophies behind Freda, right from the very beginning, is that we were going to be uncompromising. So we did want to simplify device modeling. Modeling or developing a new model for a new type of physics or even for another transistor is an enormous amount of work. Back in my early days, I did some consulting with CAD companies writing models to go into SPICE, and gosh, is that frustrating. It takes, I remember quite well, one model took me 40 major changes and 27 files, and I can never be quite sure I found all of them. But it was hard-coded in lots of various places. So one of the things we did with Freda is said, okay, we're only going to have one file for each model. We're going to regularize everything, so there's only one file where we have to change things. And it turns out you don't really have to do much code on the way. So we're in basically the fourth version of the code that we're in, and of course what you do is very much tied to the code. We're in the fourth version of the code, and that was developed late 90s, and we're in a pretty magic time. C++ was pretty well developed by then. There were a lot of templates and there were a lot of libraries. Mathematicians had got their act together during the 90s, at least as far as electrical engineers are concerned, where they started writing libraries that other people could use. To publish a paper in a math journal, you had to provide your code so people could check their new version against your version to see how things worked. And that's a result of a lot of problems in certain parts of the math community where people were writing papers but nobody could compare results together using different nomenclature, and so they kind of regularized things to try and get a common nomenclature. This is as I see it. That's probably not how the mathematicians see it. Common nomenclature, which I could read, and lots of common libraries. There's also an interesting development in automatic differentiation, which is code that automatically calculates the derivatives for you at maximum accuracy, the same accuracy as you could do it by hand. It's not a numerical derivative. And in late 90s, about 98, somebody wrote C++ code that implemented automatic differentiation in real time as your code was running, and it used function overloading to implement the automatic differentiation. So when Freda went through that architecture about 98, 99, Carlos Christofferson was the architect. He spent a year not writing any code, writing UML diagrams and things like that, making sure that automatic differentiation would work. And the credit to that architecture is that any model we wrote in 99 still works. Haven't thrown anything out. Everything still works. And automatic differentiation, the Adolph-C stuff in C++ just keeps getting better. When Frank Hart went to a meeting about 2 years ago, he was invited to give a talk on, I guess the group was invited and Frank said yes, and he gave a talk on automatic differentiation in Freda. That was the most sophisticated implementation of Adolph-C at the time. And at that time, you know, there were a lot of mathematicians working on Adolph-C, so a lot of people, we had certain problems. We had certain problems because we were solving things iteratively, you know, 100 million times. And no people who wrote Adolph-C, they only thought you'd use it once or twice, not that many times. So a bunch of mathematicians got involved and updated Adolph-C and fixed the problems that we had. So one of the advantages of using other people's libraries is that they have a bigger vested interest than you in making sure those libraries are working. And so I would say when we got into trouble in Adolph-C, because things were a little bit slow, we ended up pulling on the best and brightest in the math community, and they came in and helped us. So Freda, I would say 80–90% of the code in Freda, somewhere in that range, because the numbers change as we change libraries, is not written by us, it's written by other people. And that required some changes, and I'm going to describe some of those today. It meant that we could not take circuit theory as it existed. We had to change some circuit theory so that we could use off-the-shelf math. And I'll talk about the particular problems rather than now. Okay? So the idea was this object-oriented way of going about things. Use the APIs and what is available. You change what you do to suit it. And that's something we haven't done very often in the simulation community. Okay, so simplified divide. Ooh, almost touched it. You know, you actually can't see the screen, can you?
You can take a pen and
Okay.
point to it.
Oh, that won't do anything. Okay, so we're going to increase the scope of what can be modeled. And we're at the point now we think we can model nearly any physics. You know, we've done thermal, electromagnetic, mechanical, molecules, done quite a few things. Uncompromised commitment to accuracy. When people develop a program, and SPICE is a wonderful program, a tremendous program, when people develop code, when things get tough, they often use heuristics to get around the problem. And one level of heuristics is pretty good, but when you start putting heuristics on top of heuristics on top of heuristics, you know, eventually things fall apart. And so we said, okay, we're not going to compromise. At the moment, we're really tempted to compromise. And we're up pretty high in the hierarchy on some of the problems. You know, multi-scale problems, you could say we have to compromise there. We simply can't simulate at picoseconds when, so at the electrical time scale, if we're interested in a thermal problem, that takes seconds to settle out. We'll probably do the heuristics there, but we're in a good position to do those heuristics because we haven't got any compromising underneath. We're 100% accurate underneath. We're accurate to floating point precision. Okay. So Freda is GNU public license. Probably has to be that way because most of the code we're using is GPL. But that was a very good move because a lot of people are working on Freda in different universities at the moment. University of Illinois Urbana-Champaign, there are people there who are getting ready to get started into Freda in a big way, involving us as well. But there have been universities who've come in and out and used it. Queen's University Belfast did work on it at one time because the only way they could model some HBT transistors that they were working with. And while we haven't been good at this, you know, if you look at all GNU software, there's some effort to make sure everybody gets credit. And we probably could do better than that. You know, if you use somebody's transistor model, their name should come up flashing so everybody recognize it. Yeah. A little bit below the conscious level, just so people remember. Okay, so multiphysics modeling. So, you know, it seems pretty simple now, but if something is linear, in whatever domain it can be linear, let's treat it as a linear problem. Let's not pull it into a nonlinear problem. In SPICE, we're going to use SPICE quite a lot, because it's and I don't want to seem as though I'm putting it down at all, because it's a very old program. a resistor in SPICE, even if it's a linear resistor, it's treated as a nonlinear element. And by treating it as a nonlinear element, it means it's just going to get more and more sophisticated. Not more sophisticated, it's going to become more difficult. I was just looking at the screen there. That screen is not this room, is it? Hi guys.
It's the remote.
The remote site, okay. So I'm talking to you as well. Is that delayed or are you real?
No, they're real.
They're real, okay. Well, it could have been a picture, except they all started leaving. No. All right. And they don't like my jokes. All right. So, let me get back to the SPICE paradigm. Okay, so every element is treated as if it's nonlinear. And the rationale behind that, you know, what would have led them to that decision is the way we handle everything with circuit modeling is that we try to treat everything exactly the same way. It's the idea that every node in a circuit is the same. Whereas maybe life could be a little bit different if we treated different nodes as different things. But here we do pay a price. If we treat every linear element in our circuit as a nonlinear element, one, it means it's going to take longer because we're going to have to iterate to get a solution. And the other one is our errors are going to build up. We're going to start becoming ill-conditioned earlier than we could have. So Freda has a number of ways of analyzing a circuit. We do have this tran2, for those who've used it, tran2, which actually partitions the circuit internally into linear and nonlinear. What is linear is handled as a linear problem, totally as a linear problem. We don't exploit that very often, but we can. Okay, so the idea is only when something is absolutely nonlinear do you treat it as nonlinear. Otherwise, you pull it out. And so if this is all linear, this here was an EM defines circuit at one time. Oh, it is still EM, I guess. And we just collapsed our EM into the linear circuit. Okay. We handle a thermal network as well. When we get to that, I'll talk about some of the neat things that were done there. Normally, a thermal problem is nonlinear. Even if you've got linear thermal parameters describing your object, it's actually nonlinear, or the relationship between the heat flux and temperature is nonlinear. So I'll talk about some of the things that were done there. Okay. You know, as I said, I pulled a few slides from a lot of different talks here, and so it will seem a little bit spotty. But what I want to say here is that, the point I want to get across here is that if you write down equations for a circuit or for any multiphysics, and you go straight out and solve it, the first thing you think of is solving it in the state space. Solving it directly. You know, you write down the equations, and they may be nonlinear, but you go ahead and you solve those sets of equations. And what SPICE introduced, the idea really came from IBM, because IBM had a little internal program that was top secret, and SPICE kind of learnt a lot from that. What it does instead is it comes up with associated models. It doesn't actually solve, if you like, the set of equations that describes your circuit. It solves a related set of equations, or an associated set. No approximations, but a set that behaves a lot better. And so this is where we want to be. We don't really want to be down in the state space domain. So what does a circuit simulator do? Well, much the same as what circuit analysis is all about and what electrical engineering is all about. We look at this problem with energy storage of different types and energy dissipation, and we break it down into a collection of elements, topology, and we separate it from the way we solve the circuit. So we have this total separation of circuits from topology from the way we solve the circuits. Freda actually changes the topology that's used. Gosh, I was lucky. Oh, that's because I've got this in my hand.
I think so.
Right. That's good. I'll just leave it there. Okay. So this is probably the paradigm which fits with... Look at this, I can write too. This is the paradigm that fits with electrical engineering, the separation of circuits from the topology. It's, if you like, a way of solving finite elements using compact models, finite element type problems or multiphysics problems using compact models, rather than going off to an enormous matrix, turning it into a great matrix problem. Okay, here's the associated discrete model, and we can't really do justice here without a whole bunch of equations. But the thing is that if you're doing a transient analysis in SPICE, you will take your, say, equation describing a capacitor, so it's charge and voltage. You get away from capacitance pretty quickly. Get down to charge and voltage, and you discretize it in time. That's one level. And then you discretize it in terms of the Newton iteration step. And you've got two levels down in discretization. It's as accurate as the time step allows, but you actually solve that problem. And it's a totally linear problem that you solve over and over again, rather than solving that nonlinear problem using a very general solver at the top. Yes?
Sorry for asking something.
That's fine.
An associated set which behaves better numerically?
Yes.
Okay. So
Yes,
that's the motivation for going into the set.
Yes, it behaves better numerically. And what SPICE also uses is it uses heuristics to solve the problem. The most difficult problem you solve with a circuit is a diode, is the exponential of a diode. And we have a particular way we do it in Freda, but in the way they do it in SPICE is they make sure the current can't change by more than 10% and the voltage can't change by more than 10% from time step to time step. And that's, if you read the code, you see exactly what they're doing. They're doing a little test. But that's the heuristics they're using. Because the experience is that will solve things most of the time. Most of the time when SPICE fails, it's failing because of that exponential problem. Either there could be a problem in the way the model was written, but usually you can trace it down to an exponential. Maybe it's buried into a transistor somewhere, or it's a diode itself. But it's usually just something like an exponential. It could be a square root, or you're getting into something that's very strongly nonlinear. And SPICE uses Newton's method. And of course there are much more modern schemes for solving problems now, but we don't know how to discretize things so well if we get away from Newton's method. Yeah. All right, so that idea is really a nifty idea. We make use of it in different domains in Freda. And let's go back to a circuit. One of the good things about teaching graduate classes in advanced circuit theory and doing a lot of work in circuits and circuit modeling and then going in and teaching sophomore circuits is you realize that it's absolutely amazing how you can con all of these people in the class to accepting circuits, because it's a very deep thought process goes behind it. What Kirchhoff and his colleagues did when they came up with the idea of circuits, where did they come up with something like that? It's really quite amazing to think that you could just take a little symbol like this and use it to represent, loss. That's a pretty amazing idea, because, in those days there weren't these tiny little things that looked like dots anyway. Everything was distributed. And what was a capacitor? It was like a jar, and plates. And they thought, oh, that's a capacitor, what we think of as a capacitor. So the way we do our circuits, the way we've developed circuits, is that we have a ground, a universal ground. We think of a global ground. Everything is 0 volts at that point. And everything, well, let's go back a little bit. Okay, got rid of it. And, okay, everything is referred to that 0 volt level. So when we're building up our matrix equation, we eventually want to come up with a matrix equation. Well, there's several forms we want it, but we would like to have a matrix times a current is equal to a voltage, where that matrix would be something like admittance. Okay, so all of our voltages are referred to one ground, and then we actually even generalize it a little bit further so that we have an external current going into each terminal. Most of those external currents are 0, but we want to treat everything the same way, so that could be an external current source. So other key things that are coming out of this is the constitutive relation. So we're breaking it down. We're going to separate the element property away from the topology. So that's a constitutive relation. And here is information that just comes from topology. I'm going to talk a little bit more about topology and what a circuit is, because I spent a long time trying to figure out what this was all about. So when we do a KCL analysis or KVL analysis or nodal analysis or mesh analysis or any of those variations, this is really the big view. This is the universal view you're looking at. There's one reference terminal. We have these external current sources to all terminals. Inside we have a whole mess of connections. And most of these J1s, J2s, etc. are zero, only when we have external connections to them. Except when we're doing transient analysis, because that associated discrete modeling introduces current sources. And those current sources are a memory from previous Newton iterations. So in fact, when you get down to looking at the way you actually handle nonlinear circuits in transient analysis, you have these external current sources everywhere. And it's a linear problem, which you solve over and over again. We learnt Kirchhoff's law along these lines. So here are three, let's say, resistors that are connected together. And so we say, okay, we apply KCL to a node, and then we write down a KCL equation. I spent a long time trying to figure out if Kirchhoff really said that or not. I never could find out where he actually said it. I got it down to one paper that's in an archive, and it's written in German, so I kind of gave up about then. But I think he said this. I think...
Kirchhoff actually stated it in terms of graphs.
We're getting close to a graph.
Yep.
Okay. Have you seen it?
I know the theorems.
Oh, right.
Yeah.
That's why I didn't recognize them. They were theorems. Theorem schmearums. Right. So, this is the way Freda is working. So we'll say, okay, we put a cut set. That's actually a circuit theory term. Maybe it's a topology term. If we draw a cut set, the sum of the currents through that cut set must be zero. Okay? So it means easy enough to see with three-terminal device, we draw a circle around it, and we'd say the sum of the currents through that is zero. So in SPICE-type circuit theory, SPICE dominated a lot of the way circuits are taught. The way SPICE works is the way it's taught. We would call that a node, and we'd call that a node, and we'd call this an edge, and that edge has properties. Well, that's really messy. You come over to a three-terminal element, where are the edges you want to draw? And you wanted to call that a node, and that a node, and that a node, and then you have this edge which must have at least two parts to it. And so in the SPICE paradigm, everything is a special case. In Freda, we treat that as a node, that's a node, that's a node. So we have two types of nodes. Every element is a node, and the edges have no properties. They do have properties, I guess, very simple properties. They just connect nodes together. One of the things that is really nice about that is that suddenly you can start using the results of topology, straight out of the math department. So here's one of these ideas. So an electrical engineer is coming along, from many years ago, a few decades ago, and they say, oh yeah, I like this topology idea, but they jump straight into it and they assign a property to an edge. And this is a property that only a small group of electrical engineers needs to know about. And so you go in there with your ideas and you hack, if you like, theories coming from other places or concepts that have come from other places. Whereas what we've done with Freda, because we're able to start from scratch, is we're able to say, okay, we're going to take these concepts just as we read them out of a book, and we're not going to change them. We're going to change the way we do things to fit. And it paid off amazingly well. Whenever we got into trouble, we could go over to the math library or read a math book, and we could end up getting solutions for some of our problems. It happened over and over again. So here's a bigger version of it, of what I think Kirchhoff probably said. We draw a big cut set around our circuit, and we still have the sum of the currents are equal to zero. So this is getting us closer and closer to being able to handle multiphysics problems. Because we could put all of some type of physics in here, and then we know how to interface it to the rest of the world. Okay, that's kind of really putting all of those things together. This is a problem we were given. We got funded to do this a long time ago. We got about, probably got $2 million to analyze that problem. And so let me describe what's going on here. And the question is this a circuit? Well, it doesn't look like a circuit at all. So what you've got here, this is a microwave problem. So I'm really a microwave engineer. This is a microwave problem. We put fields in here. This is a rectangular waveguide. It's basically a propagating field, but we set the dimensions of that little opening such that only one mode can propagate. The field has a, like a half sinusoidal variation in the electric field, and it's confined. That horn, as it's called, opens slowly, and so we maintain that mode. If we just threw power in, well, it'd be a complete mess. Wouldn't be correlated. But we can, if we do it slowly enough, and usually there's an exponential taper. This is actually a hard horn which even does a better job at maintaining it. This is something that Amir Mortazawi has a fairly strong reputation for, is coming up with a hard horn. It just helps spread it out. Then we end up going into this array. This is an array of, that one's out of ink.
No, I think it's your hand being on the...
Oh, even. Okay, I shorted it out. Right.
Yes, it's basically a
Okay.
static charge.
I'll tell you. Okay. Okay, so this is an array of transistors. More or less you can say that it's a grid of bias lines and antennas, and you have transistors on the edges. So one of the problems as you go up in frequency is combining the power from multiple transistors. There's a limit to the amount of power you can get from a single transistor. And it's probably about 10 gigahertz, it's of the order of a watt or so. You can combine so many inside the same integrated circuit package, but eventually it's a case of diminishing returns. There's so much loss in the combining network. So the idea of this amplifier, which is called a quasi-optical amplifier, and there are commercial products at the moment about to be released by the people who worked on the same project, is that you combine them in free space. Combining power in free space is lossless. This is actually a diamond heatsink. There was thermal issues were a really big deal. And by the end of the project, we could model that. So we had to do electromagnetic solutions. We had to get the thermal and the circuit right. In fact, this is the particular version that we got working. So this circuit was built up in our lab here. There were quite a few of us involved in that at the time. So this is built up in the lab. There are amplifiers. You can see a little amplifier in that region there. These are patch antennas on the way in. Here's a horn, there's a horn. And the best we were able to do was this. We have the measured result and the simulated result for a structure that doesn't look like a circuit at all. Well, that was modeled in Freda. It includes electromagnetic, circuits, thermal, so multiphysics to some extent. And we could do it. We had to change the way the electromagnetics was done. We had to solve the electromagnetic problem so it would interface with the circuit problem. That was one of the developments that had to be done. So it can be done, and this is an amazingly complex piece. There are some things that exist in life that we cannot model in circuits. There is no circuit equivalent. And we do have problems modeling certain types of transistors. And I tried to boil down where the problems are down to the simplest case. So here's one case. We have something like a vacuum tube. We're going to set electrons off. They're going to drift across the open region, and we'd like to be able to solve that. But if we draw a cut set around that and we sum up the currents, we'll see that they're not zero. Physically, they won't be zero. So we will not, I4 of t is not equal to minus I3 of t. It's actually delayed in time. Our circuit theory can't handle that problem. It's something for the future that has to be solved. I would say that the main reason why we have problems modeling a lot of things, in particular modeling transistors, is that we're trying to model them with physics which isn't right, or we're trying to model them with equations which doesn't really capture the physics. So, doing multiphysics with compact models can't solve everything. We just don't understand this business of charges accumulating or charges being caught in a diffusion region for a while. Okay, I probably need to pick up the pace here a little bit. Network graph, this is the graphs that I described before. There's a circuit graph and a network graph. This is the form that Freda uses. This is the version that SPICE uses. And how we would go about doing transistors. If you follow that, let me go back here again. If you follow that topology, you can actually develop a UML diagram to lead you, best to do a UML diagram before you write a big C++ program, to guide you to developing a C++ program. You have nodes in your graph. Everything about graph is just as you read out of a great math book. You don't have to change any of it. And it fits into this object-oriented paradigm really well. You only need to know the UML diagram once, and that's when you're planning the program. I think once you got it working, you forget about it. That's certainly my case. You can do the same thing with analyses. So I should go back one slide here. This element, the code for an element, a particular instance of an element, I should say, that code for a particular instance of an element is one file, and usually pretty small. And I'm actually going to give you all the code for one of the elements in a little while. If you want to stay till about 6 or 7 o'clock, we'll be able to go through it line by line. We can do much the same thing with analyses. We were not able to get the analyses into a single file. If we had another few years or a PhD to spare, we could probably think through that and put all of our analyses into it as though it's a single file. And we have about 31 analyses. The very first analysis we did in Freda. Does anybody want to guess what the first analysis was? Those who already know, you can't tell. What would be the simplest analysis you could think of? DC? No, the first one we did in Freda was wavelet analysis. So, because our sponsor said, I think there's a lot to be said for wavelets, and I wanted to do wavelets. But looking back on it, it was the right thing for us to do because it was so different. So we had to first of all figure out what wavelet analysis meant. And we read all the image processing books, not all of them, but some of them. We said, no, I don't think that works. And so what we came up with is this idea that we solve multiple time points at the same time. Don't try and get the best solution at a single time point. Pick a whole range of time points and get the solution for those all at the same time. Some parts of the circuit don't need every time point. You could skip time points for parts of it. So that gives you the multi-resolution aspect. But what that meant is that Freda didn't know about currents and voltages to begin with. It was just dealing with abstract variables. And fortunately, that meant we're in a better situation to handle multiphysics because we weren't tied into the current and voltage view of the world. Okay, now here's another interesting concept. This one took us a long time to come up with. Okay, let me describe this. So here's a transmission line. We can do a similar thing with a transformer. If you don't like transmission lines, just consider that we have a transformer here. Okay? So our idea is that we push current in to one side, and we have an equal and opposite current coming out here. Okay, I and I. Equal and opposite. That's what we'd get with a transformer, what we get with a transmission line. It's actually something extra that we're adding to the problem. We could say, okay, well, and a similar thing over here. So we have a current, say, I dash, and a current I dash coming out. This is a port. I mean, it's easy to call it a port if you're a microwave person, and we call it a port. We could have come up with some other idea. But we have a port here. Now, how do we put that idea into a circuit simulator? Well, the idea we came up with is to add local reference terminals. Well, have I written that? Oh yeah, I got it over there, local reference terminal. So we had a local reference terminal here and a local reference terminal here. So if we do a cut set around this, those currents have to go to 0. So it's a special element, spatially distributed element, and we have these local reference terminals. Okay, so we can go up to a multi-port version of this. So this is where the multiphysics comes in, because each physics has its own reference. We don't have to have a global ground which is supposed to handle thermal problems as well. And so the sum of the currents across all of those terminals must be 0, because it's a locally referenced group. So we didn't do that because we wanted to handle multiphysics. We did that because we wanted to be able to handle problems such as a transmission line, but it turns out it was just the right thing to do for multiphysics. Okay? Now we actually did experimental work. We were trying to model that quasi-optical amplifier. We did experimental work and we couldn't see why our simulator didn't agree with our measurements. And of course you doubt your measurements because you're trying to measure at a few gigahertz. But that happened to be the answer. So this is the way we handle a circuit. So here's a transformer. So transformer on top of each other. The way we would handle it in SPICE, we would have to connect this together in SPICE. We can't have two disjoint circuits. But Freda is really happy. We just have a local reference terminal for each side. And Freda just chugs along quite happily. Of course, we're going to have different physics. Generalized import, we can just go on and on. Okay, here's another idea that makes this work. I said before that the exponential is one of the big problems in SPICE. Okay, and we end up having heuristics to handle the exponential. We make sure the current can't change by more than 10% and the voltage can't change by more than 10%. Well, we wanted to use off-the-shelf math, and we didn't want to use any heuristics at any level. And if we're going to use heuristics in the case of a diode, it means that we have to treat the nonlinear solution for each element separately. Okay, that's kind of seems like a small deal, but that's an incredible job. So SPICE, it's very difficult to add an element because any of the elements that are worth adding now are very strongly nonlinear, maybe a transistor, and so you have to dig inside and do some heuristics. So what we did, we came up with this idea. Actually, we borrowed this idea from somebody who used it in another application, and he called it parameterization, where you take a strongly nonlinear function, here the I versus V function, and break it down into two well-behaved functions. So you introduce an intermediate variable x. So I here, well-behaved, the derivative is always well-behaved on both sides, but still I as a function of V is okay. So we iterate on x. X is the unknown. So when we're doing our nonlinear solution now, all of our nonlinear problem is well-behaved, there's no strong exponentials. We could take this idea and apply it to other parts of the problem we're analyzing, but we found that we only have to do it to exponentials and nothing else really matters. The exponential is the difficult thing. A universal error concept that you need, we had this idea that we don't do KCL. We actually do the equivalent of KCL, which is saying we sum the fluxes at a node. So we guess our x's. Everything has an x. We guess the x's, and from the x's we calculate the equivalent of flux or current and flux and potential, or current and voltage. And we say, well, the sum of the fluxes must be 0 and all the voltages must be the same. And what that is we're actually doing an energy minimization, or an energy norm. We're not just doing KCL equal to 0, which ends up being a problem if we're trying to handle things like CMOS circuits, because they could be in a state where there is no current. And so, but no problem, we're just handling energy. It's okay if all the currents are 0, because something else isn't 0. In the electrical world, our flux is current, our potential is voltage, and our local reference node is our local ground. You know, we no longer have to have one ground. In thermal, it's heat, current, temperature, and absolute 0 temperature, the things that come out. And we really like this one about mechanical. Flux is force, potential is position, and the local reference node is the inertial reference frame. So it's amazing how it comes out that way. And this is actually different from the way the VHL, the hardware description language, VHDL is written, or is it Verilog, it's one of those. They actually have velocity here instead of position, but it actually doesn't, we can't do an energy norm on it. We need to have position for that potential. So what we're saying is, if two objects are pushing against each other, the sum of the forces at the interface is 0, and the position of that intermediate node, well, it always must be the same. So we did some mechanical modeling at one time, but you know, we lost the code. Well, we really try hard to make sure there's only one source tree, but we actually lost the code for our mechanical models. That's the only thing we've ever lost. I want to give you an idea of some of the difficulties that we're dealing with. See you later. Okay. Some of the difficulties that we're trying to deal with. So if you are trying to work with cellular phones, you have to design your output amplifier to produce as little distortion in the neighboring channel as possible. So this is a digitally modulated signal. This here is the main channel, and over here are the adjacent channels, and the specs are that you must introduce distortion that is at least 80 dB down. And so one of the ways to get an idea of what this is like is to think about the number of pixels on this screen. How are we going for time? 10 minutes, okay. So we have about, 1,200 pixels that way, 1,000 pixels that way, and it all works out that we want to be able to simulate distortion which is equivalent to 1/13th of a pixel. So it is incredibly tiny. You need incredible accuracy. So that was another problem that we had to address in Freda. We changed the time stepping algorithm. Basically we do two different solutions at every time, nonlinear solutions at every time point, and compare them. And that's pretty novel, and it ends up giving us great dynamic range. That was a soliton. This was another problem that we had to look at a long time ago, is to model a soliton line, and a soliton line ends up producing, a pulse that's a few picoseconds wide from a source that is really much lower in frequency. That couldn't be modeled in any other simulator. So, pity I didn't put numbers on this, isn't it? So nonlinear electro-thermal element. Let me go quickly through the way we handle electro-thermal elements and the way we have a number of novel models. Okay, so here is our this could be a transistor. The transistor has an electrical part and it has a heat part. Multiply current and voltage together and you get heat generated inside the device. It produces a heat current, thermal network, linear electrical network over there. So we've got some thermal modeling. So being a microwave person, in order to publish in our literature, we have to do measurements. That's another thing you learn when I was editor, of course, is that every different discipline has its own standards for the way you publish a paper. Some you have to have incredibly detailed computation. You've got to compare it to somebody else's incredibly detailed computation. In the microwave world, it is measurements. We don't care about the theory too much, it seems. That's important. But nobody really believes you unless you have a measurement. And so we've done quite elaborate modeling. Here's a mimic. We put black ink on it and did a thermal image. And what this is basically saying is we could predict the temperature pretty well. And we can even get down to the individual fingers of a transistor and measure the temperature there. This is work that we are involved in at the moment, quite a few people in this group. If you're going to look at integrated circuits at the moment, one of the biggest challenges, well, we know what one of the biggest challenges with integrated circuits at the moment is that we're getting to the ends of Moore's law. The dimensions are getting to basically getting as fine as you can. TI has decided they're stopping at the 45 nanometer node. They're never going to go any further. And so we're at the point now where people aren't going to reduce their lithography much more. Maybe 32 nanometers, maybe a little bit more. What Intel, IBM, Texas Instruments, and on are saying is they're going to start doing 3D integration. They're going to take 2D circuits, thin them down, and stack them on top of each other. The major limitation is temperature, is the thermal profile, because everything is getting really hot. Even in 2D, now you start putting them on top of each other, it gets even more. So for quite a few years, going back to about 99, we've been working on thermal modeling with the University of Leeds and here, although it's mostly here now and moving into Urbana-Champaign. Okay, so we have a model for 3D ICs. We can simulate this model. We're at early days yet, but this is to give you an idea of some of what's going on. This block is modeled, remember this is thermally nonlinear. Even if all the thermal parameters are constant, like heat capacity are constant, this is thermally nonlinear. And silicon dioxide and gallium arsenide are thermally nonlinear. Those parameters are nonlinear anyway. So you find these are really quite nonlinear. So there was a fellow, Bill Batty, who was at the University of Leeds, who came up with this incredible concept. He did a couple of it's amazing how it finishes the lines too. This incredible concept whereby he was able to take this problem, which has only been solved volumetrically. He took it out to the boundaries He did a couple of transformations. One of them is Kirchhoff's transformation. There's another one which doesn't have a name, which turned the problem into a linear problem. Yes, there's distorted temperature and dilated time, but you can fix those at the interfaces with the next element. And so we can analyze very large blocks in almost no time at all. Instead of the 2 hours that it would take to use a finite element solver, we can do it for 5 minutes for the first time step. So if you use a commercial finite element solver, it is about 2 hours per time step. We can solve the first time step in 5 minutes, and then the other time steps are the same time as analyzing the rest of the circuit. So if you sit back and you think long enough and you're given enough time to come up with a solution, try and turn your problem into a linear problem, and things will also work a lot faster. So some of the things you'll see, this is the heat rise in silicon with just a step heat source. This is logarithmic at the bottom. This is a long tail effect. People are starting to see that and wonder what's going on. We've got some work going on in the group which says, okay, we need fractional derivatives to describe that. So we ended up getting quite involved in fractional calculus, much more so than we'd ever want to, because we want to come up with analytic models for this as well. So these are very hard to see. This here is an inverter. So there's a little inverter on there. So this model is what was implemented. Here's an inverter with the voltages going up and down. These are the heat sources. So the heat occurs, of course, when we have current and voltage at the same time. So there are spikes, very tiny. And this is the differences in the temperature. This has been changed a little bit just so that you can actually draw a graph of it. Our biggest problem is how can you model this when things are happening in the circuit at the picosecond time scale, but you need to model it for a few seconds. So that time scale, handling 2 time scales is very difficult. Modeling scope, I know we're just about out of time here, so I'm not going to talk about this. Basically, we can handle much more than you can in the SPICE paradigm. Electro-thermal resistor code, I said we'd go through a lot of code at the end. This is just handling electro-thermal resistor. I will show you where the executable code is. This is the only executable code. It's 5 lines. The rest are mostly comments and boilerplates. Those 5 lines would compare to about 500 lines in SPICE. So a great change. Going to go through a few models very quickly here. We have handled many different models. Long time delays, not a problem. You have to sit and think for a long time as to what the error function actually will be. This is quite different from that problem we talked about earlier where charge accumulates in a region. Noise, model flicker noise, 1 over f noise. It's different physics. And the way it is done is by introducing a stochastic solver in Freda as well. So it's not just a deterministic solver. It has stochastic differential equation solvers in there. An optoelectronic system. This is totally different. Some of the variables here are wavelength, numbers of photons, and energy. And so not quantities that don't look like current and voltage at all. The ray tracing was actually done in an output routine. And with that, that'll be my last slide. So Freda is GPL. There are a lot of people at NC State who really want to help people use this if you're at all interested in using it. And our mission at the moment is to get other people adopting it. And so far about 6 different universities have played around with it, either used it for a little while and left. It looks as though a couple of places like Georgia Tech and Urbana-Champaign are getting much more involved in it now. Okay, well thank you for your attention, and I guess if we have any time we can have questions.
The questions first, I guess we should let the remote side ask any questions if they have any first. All right, okay. If not, then we'll take any questions here. We have a few minutes for questions. Yes.
It says there's a MATLAB interface. How long has that been around? Has there been other interfaces prior to that one?
MATLAB interface is fairly primitive. Justin wrote it. Well, you know it works.
Yeah, it does work. There's essentially you're just calling the MATLAB inside the code. with the API now.
Yeah, we don't quite know what to do with it yet. But Freda, you can change things incrementally in Freda, and one of the ideas was that we could end up using the optimization loops in MATLAB. You know, it could pass across updates. And if you want to change a variable in Freda, you can just say, I want to change, because Freda's got lots of variables. You can end up changing a variable, and it knows where to change. It keeps track of where the variable has been used. So, and it does equations, calculations as well. But I think we're interested in trying to do some graphics in MATLAB, but now Freda has its own GUI. And it's sort of like a schematic. It has its own schematic capture engine. Justin's very responsible for porting a GPL piece of software over and modifying it to get the Freda syntax. And the MATLAB version, well, you know, we don't really want to write things. If we can use somebody else's optimizer, we will. Freda doesn't have an optimizer in it. It solves nonlinear problems, but it doesn't have an optimizer. And so we were hoping that we could just make use of MATLAB for that.
Any other questions? What does Freda stand for exactly?
Absolutely nothing. Well, just like everything else about Freda, we worked out what it meant afterwards. So I don't know who said free EDA, but I guess it does look like that. No, it is a matter of finding a website.
I see.
Yeah, the name previously was Transym, and this is a very good lesson. Some people called a program, and they wrote up a description was just like Transym, and they registered the trademark.
Oh, yeah.
And so we had to get away. And we went back through our literature, and wherever we used Transym, we never put TM. If we'd put TM, we would have had the rights to keep using it, but we didn't. So now when we use Freda, we put TM everywhere. So if you ever have something which you've given a unique name to, just put TM after it. And that is better than registered, because TM is worldwide. Registered is just the country you're in. So if you have a name which you want to mean something. So we're a little bit upset about that. And so I went through all the names, a book of names are all taken, and just added an extra E, and it was, so yes, it's basically websites drive names.
Great. All right, if there are no more questions, let's thank again our speaker.
Thank you.
WCU, I saw that you connected. If you want to come on out and talk to me, I'll talk back.